how things are going on? Yeah, still don't want to run away from university? Still want to study, yeah? Okay. Uh, so, two comments I have for you, uh, mostly based on request I got recently. So, first comment about textbook. Unfortunately, this printed textbook you cannot take with you home. So if you really want to work with the textbook, you have to do it in the library. So that is the information about the textbook. So unfortunately, you cannot add it to your package, so you can pick it up and take with you home. Uh, Another thing is there were some questions about this Try Me quiz in Moodle. So some of you guys still do not have this Try Me quiz in your Moodle. When you log in into your Moodle account, go to this Physics 161. Just below the announcements, there should be Try Me like active link where you can go. So this is a quiz, as I mentioned earlier, which will allow you to practice solving problems in Moodle, so to avoid some potential issues in the future. So that's if that is the case in your Moodle account, please contact IT department and let them know about this. So these issues mention that you are taking this class Physics 161 and you are not properly enrolled into this Moodle system. Because you will need it to practice. It's not so critical to have it right now, but in the near future, definitely would like to practice with this Try Me account. So, if you have any questions regarding organizational work of our course, you're welcome. If not, then we can proceed further and start with our topics. So, physics is some fundamental natural science which tries to understand the nature, like processes which happen in nature, matter, which nature consists of. So it's kind of very broad definition. Obviously, here we will consider like start with mechanics means we will deal like classical mechanics. So we will deal with behavior of some macro objects which will interact with each other, and our questions which we will going to answer will be what will be the position of somebody over some time in given system of references, how fast it's going to move, what is the reason for this motion, and things like that. So that is our like beginning, like first steps into mechanics, and we will start from some element like point objects, and then we will go to extended objects involving not only translational but also rotational motion and things like this. However, we need to introduce certain so-called dimensions and also mention about units first, because all this is quite important. So that will be the topic we will cover today. And let's say if we have this table, what kind of parameters, like features of this table, we can highlight? So it possesses some mass. That is correct. Obviously, it made from some material, in this case, some plastic and metal, and that will this object will possess some mass. So Another feature. Okay, so lens. So all these features are kind of important, but in terms of, let's say, what we consider in scope of mechanics. So the size and shape of this table matters. So we need to deal with either height or width or length. So in any way, we call it length. So that's the dimension length, which so we have the one dimension mass, another dimension length. And what is important dimension defines the physical nature of the parameter which we consider. So if we have some quantity with some dimension, so we clearly know to which kind of feature this dimension belongs and what it describes. So we cannot compare quantities with different dimensions. So for instance, if we're talking about mass and height of this table, we obviously cannot compare them because they possess different dimensions. They possess different physical nature. So it doesn't make sense to compare them. Another dimension which is critical for our work in scope of mechanics is time. So for instance, if we start to move at some given conditions, we move this table from point A to point B, and then there will be some time interval which will take us to move this object from point A to point B. It doesn't happen instantaneously. We don't have teleportation of physical objects. So there will be some time interval. And this another dimension which should be taken into account. So let us highlight it here. We have first mass, then we have length, and we have time. So capital M, L, and T, those define their dimensions of which are relevant for our consideration in the scope of mechanics. So, okay, we have dimensions. We know the physical nature of the parameter. However, we also need to quantify. So we need to provide some reproducible and accurate way to quantify this, because let's say if we compare these two tables, like table 1 and table 2, obviously the table 2 is larger. However, that is qualitative approach. We only qualitatively can make a statement that table 2 is larger. We cannot, without introducing certain units of measurement, we cannot make any quantitative statements. So what kind of units for measurement length do you know? So yeah, we started from meters. So in the international system of units, meters is the unit for length. That's correct. But also other units which you mentioned, they also are true. Either some derivative of meters, we have centimeters, kilometers, but also there are different units like inches, like miles, and they are quite widely used in the world. So they are different. It could be quite confusing, but if correctly keep all this relationship between units into mind, we will eventually have the same results. It's just the thing that different units are accepted in different countries and communities. For instance, how it started. So obviously, at some point, people wanted to have some standard unit for length. And then how to do it? Imagine some Asian kingdom. You want to introduce some unit of length. and want to still have your head on your shoulder, so king is happy, you probably introduce some length of king's foot as a ettalon, and that will be the unit of measure. So that's an option, but that's not very reliable because things are changing and their foot lengths also may deteriorate over time. So then next step was to introduce some physical objects, let's say some reliable, I don't know, some stick, metal stick, for instance, and define what this stick has a length of 1 meter, let's say. And that will be our standard. So we will calibrate all our equipment, measuring equipment, with respect to this piece of metal. And that works way better, quite more stable metal stick than king's foot. However, what if, first of all, someone steals this stick? It disappears. Second, there is some linear like extension or like change of linear size upon heating or cooling. So if the temperature is different, the length will be also different. So means that you need to keep all this the same conditions, which is not so trivial to realize. And then you calibrate your devices with some unit which is not constant, means your different devices will measure with different accuracy and will provide some systematic errors to measurements. So the goal, those standards for units, for instance, for meter, is actually a very long process for all SI units. They are always revisited in terms of improve the accuracy of their determination and the reliability. So you don't want to rely on some physical object with in terms of length or mass, because these physical objects, they can change their properties, they can disappear, different things can happen. Plus, if you move to another planet, gravitation will be different, then probably length of the object can also be different. So it's not good idea to stick to some physical object. It makes more sense to stick to some fundamental constants and fundamental features which will not change, never, regardless on the position of where you want to double check this unit. So it was probably recently, I think, like in 2019, last time length, mass, and time units, international units were reconsidered. So we will not go into the specifics how they are defined. You can read about this separately. Just need to understand that this is a continuous process, and we always want to make it more accurate and more reliable in order to rely only on some fundamental things which do not change regardless of any conditions. So another thing what is very important, we mentioned about it. So yeah, and also of course we have one more dimension, it's time. So in international system of units, it's second. So it's very important to be sure that the conversion between units is correct. So and which units you are using, because different things happen as a result of this misinterpretation of units. Either you come to, like, for instance, European tourists come to United States and pick up in grocery store some packages with fruits and vegetables, then go to the cashier to check out and eventually have to pay more than twice they expected. And that's only because they didn't pay attention that prices were per pound, not per kilo. So that is quite relaxed situation. But in the history happened quite different things. For instance, in 1983, Air Canada flight, when they made the shift to international units, at the beginning of this shift, they had an accident with their flight when they had to turn around in the middle of their flight in order to land as soon as possible, because they figure out that the fuel tank was empty, and that was after like investigation was done. It was clearly that the reason was just this transition from between systems of units, and was incorrectly calculated how much of fuel should be added to the fuel tank. Another example, NASA lost its 125 million uh, satellite, which supposed to investigate weather, like climate, on planet Mars. Also because misinterpretation of these units, because the flight control unit of NASA was using different units as one of their subcontractor when they designed the flight control system for the satellite. So things happen, and obviously this could be avoided if you take care about units. That's why 30% of your answers for solving problems will originate from correct units. So please be aware of this. So now let us come back again to dimensions. And there is such thing as dimensional analysis. So it's quite useful, first of all, to double check if your solution is correct. So every time when you do some, you solve a problem, you derive equations, so you want the ideal way, which saves you a lot of time and let you make less mistakes, is to derive final equation and then just substitute the numerical numbers there. That means that you will have less steps, and the chance to get some technical errors goes down. However, you need to be sure that your derived equation is correct, and dimensional analysis is very good, because we mentioned that we cannot compare two quantities with different dimensions because they possess different physical nature. What does it mean? It means that if you have some equation and there is some left side of this equation and right side of the equation, dimensions of left and right side, they should be the same. They cannot be different. If they are different, means you made some mistake in your derivation. So if, for instance, we write here that we have m in the power of a, l in the power of b, and t in the power of c, and that is equal to m in the power of x, l in the power of y, and t in the power of z, then what is your suggestion? What should be values for x, y, and z? A, B, C. Yes. So that is the golden rule you need to remember in dimensional analysis. Left side dimension should be the same as right side dimensions. And another thing, what is good for this dimensional analysis, is when we want to make some prediction in the field which is not yet established, so we are not sure exactly, we don't have enough information about the system of our interest, but we can make some estimation what parameter will make a difference, what parameter actually matters in our system, and will define the feature of our interest. And then dimensional analysis can help us to get some relationship between parameter of our interest and parameters which we know. So it can tell us what will be the dominant parameter which has the most influence on the unknown parameter, and also can show us the behavior, like in terms of some equation, some dependence of these parameters on each other. The thing is that it will not give you the exact analytical solution, obviously. So this equation is not final equation which will accurately describe parameter of your interest, but it will give you with accuracy this equation with accuracy to some constant. And that is quite helpful because you can make a rough estimation initially that can really help to define some direction of your research in certain project and figure out which of many parameters involved will be the most important in your case. So let us consider one example, and that is let's say we have some system with some object is moving with constant acceleration. So we will derive analytically this next lectures. But now we just, with the help of dimensional analysis, will try to figure out what will be the how this dependence will look. So let's say we have some position x, and we have object which moves with constant acceleration a. So obviously position will be proportional to acceleration. So it makes sense, just some common sense. What else? We also kind of common sense that time will also be an important parameter here, because the longer it takes, the larger the object can move. So it should be also in this equation. So we have two parameters, acceleration and time, which at some level define the position x. However, we don't know how exactly these parameters influence. Is it like this, or we have some stronger dependence on time or acceleration? So here we can write some, I don't know, let's say what we use here. We can write, let's say, n and m, and m. And we don't know this power, n and power m. So let us consider what is the unit for left side of the equation. So, well, not unit, but dimension. So here is x, its position, and dimension will be length by capital L. So what will be the dimension for the right side? So here we have acceleration, a, and dimension for acceleration will be L divided by t squared. So if we consider, just let us make it more clear. Let's say if we first consider speed, so we will introduce all these parameters in the future in details, but now for dimensional analysis, let us make it more clear. So let first consider speed. So speed is some distance which was traveled by the object divided by interval of time. So we have dimension in the numerator L, length, divided by t. Or it can be written as L in power 1 times t in power minus 1. So that's how we get these dimensions of the physical parameters. And acceleration is the speed of change of speed. So we need to divide length by time once more. So it will be L divided by t squared. So eventually we can write here that acceleration, dimensions of acceleration is L in the power of 1, and here will be T in the power of minus 2. In the same manner, we can also write here that it will be T in the power of 0. So it doesn't mean anything, will be just unity. We also have another parameter here, which is T, and that its dimension is just time. So capital T. So now we can write our dimensional analysis equation. Means we need to equate left and right side of this equation. So left side will be L times T in the power of 0. That's equal to L divided by T squared in the power of n, because that stands for acceleration. So these are dimensions for acceleration, and times T in the power of m. That stands for time, T. So now if we open this, it will be L in the power of n times T in the power of m minus 2n. And so this is our right side, and our left side will be L power 1, T power 0. So now we have two dimensions with two different in left and right side power next to these dimensions. So let us first consider dimension length. So, and we can write this equation. So 1, which stands next to L in the left side, is equal to n, which stands to the next to the L in the right side. Now we write for time dimension, and that is 0 equal to m minus 2n. So we have system of two equations, and we already know that n is equal to unity. We can substitute this in second equation, and for m, it's equal to 2. So with this, we can come back to our first suggestion, which is based just on common sense. We didn't have any experimental data on this matter. We just assume that position is proportional to acceleration and proportional to time. So now we see that n next to a is equal to unity, and m next to t is equal to 2. So we can write that x is equal to a in the, just we don't write it, then 1, we can skip it, and then times t in the power of 2. So here is some mistake. We also need to get rid of equal, because we have just proportional. Again, it doesn't give us the exact solution, but gives us some general dependence with accuracy of some constant. So that is our solution. And with this prediction, we see that time actually is more influential parameter than acceleration, because time we have in second power here as opposite to acceleration. So we didn't know it before. We still so far don't know exact solution, because in few lectures we will derive it. So it will be x equal, in this case, a times t squared divided by 2. So that is the correct equation with 100% accuracy for this particular case when we have a constant acceleration of the object. However, this dimensional analysis gave us with accuracy to 1/2 the ability without any information about the system to actually learn about it and define the most important parameters and behavior, how this parameter position x will depend specifically on acceleration and time. So this could be helpful in different cases, and specifically at the initial stage of your project when you don't know much about the system, but with dimensional analysis can be helpful to consider this. So another thing what we would like to probably consider, another example with dimensional analysis, is to estimate pressure inside our sun. So let's say it's not so trivial question now because it's not so easy to answer as in the previous example. However, we can make some estimation. So what is the origin of energy produced by the sun?
Energy? Chemical reaction.
No, that's not chemical reaction. That's too hot for chemical reactions. That's already on some nuclear level. So we have thermal nuclear fusion. So we kind of put together two protons which are positively charged and they repel from each other. But because of very high kinetic energy, high temperature, they can interact and form already heavier elements and like nuclei and expel a lot of energy. So that is the process which requires very high temperature and pressure. And obviously, in order to keep such hot substance in the center of the star, you need a lot of pressure from outside to have this steady state process. Our sun is quite stable. It doesn't change its brightness from day to day. So this is a very stable system. So obviously this high temperature, high energy in the nuclei should be compensated by very high pressure. So now let us say what parameters of this from those, let's say, which dimensions which we consider in the scope of our discussion would matter in the case of such parameter as pressure inside the sun. Mass, exactly, and length. So length, let's say, is like radius of the sun. So this obviously should be there, and we can write that pressure P will be equal to mass of the sun and radius of the sun. So also we should add here gravitational constant because obviously that will define the gravitational pressure of all this material which forms this mass on the center of the star. So gravitational constant G. So now we don't know how exactly these parameters will influence. We could not make an experiment where we create different stars with different masses and different radiuses and measure pressure inside and say, okay, this is the dependence. However, dimensional analysis can help us in estimation of the dependence what we have. So let's put here x, y, and z. So it will be x, y, and z, which are unknown at this point. So dimensions for left side and right side of the equation which we have here. And again, sorry, that should be not equal. This should be proportional. So we have dimension for pressure, and that will be mass in the power of 1, L in the power of minus 1, and T in the power of minus 2. And that will be our left side. And right side will be, so dimension of this constant G, gravitational constant, that will be mass minus 1, L in third power, and T minus 2. And when we have two more parameters, that will be mass of the sun, which actually is just mass dimension, and radius of the sun, and that is length dimension. So now we can write our dimensional analysis equation. We can equate units, dimensions in the left side of the equation to dimensions in the right side of the equation. So that will be m in the power of 1. Let me check here. Yes. Times L minus 1 times T squared. That is equal to, we need to keep in mind this x, y, and z, because we don't know them, but we need to put them here for dimensions. That will be m minus 1 L in third power times T minus 2 in the power of x. So that is for gravitational constant G. Then times to m, which in the power of y, that's for mass of the sun. And we have dimension for radius, it's L in the power of z. So now when we transform this right side of the equation, that will be m in the power of minus x plus y times L in the power of 3x plus z, and times t in the power of minus 2x. Kind of opens this parenthesis. So now we have, as we started from the early beginning, we have MLT in the left side and MLT in the right side. So we have the same set of dimensions, but they have different, next to them, they have this unknown parameters as like power x, y, and z. And we know that they should be equal to each other. Yes, you're welcome. Okay. Minus 2, you mean here? The left change for P. For P, okay. Yeah. Here we wrote e to the power of minus 2. We don't present. Okay, you mean here? Yeah, we don't. Yeah, correct. Good, thank you for following this. That's important. So we need to put it here, minus. Yes. And so now let us see what we have. Let's check around M. So we have unity equal to minus x plus y. Does it make sense? So we have mass dimension. We check what power we have next to mass, and those, they are equal to each other. So second will be length. So for length we have -1 equal to 3x plus 2. So this is our L here and here. And now let us check for t, for time. That will be -2 equal to -2 times x. So we have this system of uh, instead of 2 we have z, exact. Yes, I see that somehow we lost our unknown parameter. Yeah, so this should be z. So when we solve this system of equations, three equations, we have x equal to unity, yes, then y is equal to 2, and z is equal to -4. So now we have solution of our dimensional analysis equation. Keep this in mind, and we need to recall from what we started. We started with this suggestion for pressure inside the star. So now let us substitute instead of x, y, z, this their values which we determine. So let us do here. So we get P, pressure inside the star, like let's say our sun, will be proportional to G, gravitational constant in power 1, so we just don't write it. Then we have mass of the star in power 2, and we have radius of the star in power minus, well, actually it's -4, so we just put it in the denominator. So that is our final equation, which we get from dimensional analysis. And here we see, first of all, what parameter among those which we consider is the dominant. Obviously, that will be our radius. So because it goes in the equation with the highest power, it's power of 4, twice larger than power next to the mass of the sun. So obviously, so now we can look at it and say, okay, our suggestion initial that it will be proportional pressure to radius is not correct. So this dimensional analysis actually also takes this into account. It's reversely proportional because radius stays in the denominator of this equation. So now means that if we increase mass of the star, obviously there is more material which will push down on the core of the star and increase pressure inside. However, if we keep mass constant, if we don't change it and increase radius of the star, that actually results in a very rapid reduction of the pressure, since the density of the star will reduce. We increase volume quite dramatically with increase of radius, but mass remains the constant. So that will result in very rapid reduction of pressure inside the star. So with such approach, as you see, we didn't know anything about stars and like parameters, like processes which are going inside. So this very general understanding. But even with such qualitative understanding what the process is, we can end up by means of the dimensional analysis to an equation with, of course, with some accuracy up to constant, which with good trend describes the such parameter as pressure inside the sun. So if you are interested, later you can substitute in this equation parameters like values for gravitational constant, mass of the star, and radius of the star, you can of course deal with our uh, sun and get like estimated value of pressure inside. But keep in mind that you should substitute everything in SI units, so just to be sure that you get the right answer. Okay, if you have any questions, you're welcome. If not, I thank you for attention and wish you good evening. See you on Friday.